Okay, so that looks okay. Okay, so I'm going to tell you about some experiments we were given the opportunity to carry out last year here at Cambridge on bifurcation phenomena in pipe flow through a sudden expansion. I work with Tom Mullin at Manchester, at the Manchester Centre for Nonlinear Dynamics, and I'm not going to tell you about transitional turbulence like the workshop suggests I might, because Tom discussed that rather well yesterday. This is in collaboration with Andy Seddon and Mick Mantle. They both work at the Magnetic Resonance Research Centre here at Cambridge, which is about 500 yards in that direction. Okay, here's the geometry we're interested in. We've got a parallel pipe of some length, and at some point along the length, we're going to double the diameter through a step function. This is a sudden expansion. I said double, it can be any step size at all. We are looking at a 2-to-1 expansion. And the reason we're interested in this is because of its applications across the board, really, in industry, biology, heat exchangers, combustion chambers, stenoses, and also for fundamental interest as well. I've written up here that we're interested in fully developed quasi-flow in the upstream pipe, and the reason is, you can imagine here where I have separation, if I had a plug flow, certainly plug flow experimentally is very difficult to reproduce, and any noise at all will be amplified here. So we want upstream quasi-flow as well. Now, this problem has been investigated for a very long time by very many people. I'll just explain the schematic here. My Reynolds number is defined by the mean flow speed and the diameter of the upstream pipe. And we have quasi-flow coming in, we have separation, and we get this encapsulated recirculating eddy in the corner, and it reattaches further downstream. Now, people who have looked at this experimentally are listed here. This is just some of them. It's by no means an extensive list, but I'll start up at the top and work my way down. So in 1972, people were interested in this problem with a plug inlet flow, and they're interested in instability that may happen down here, and using simple visualization, they found that as you increase your flow rate above 359, you get something they call varicose fluctuations down here in your shear layer. It sounds rather quite exciting. If you go below 359, you actually find your reattachment point moves up and down as well. In fact, they never find a regime of laminar flow down here. They never find a case of no instability, I guess, until they turn their experiments off. 3 years later, Feuerstein, Pike and Round used a high-speed camera and seeded flow. I guess this is a precursor to PIV, with a fully developed inlet flow, and they didn't find any instabilities at all for Reynolds number up to 1,000. 8 years further on, Srini and Strukowski used hot wire anemometry with a fully developed inlet again, and they found that the reattachment point starts oscillating up and down when you get to Reynolds numbers of greater than 1,500. Again, simple visualization, comparing fully developed and plug inlet flows, you can get small sinusoidal waves in the shear layer for Reynolds numbers greater than 750 in the fully developed case, greater than 617 in the plug case. And again, 13 years later, just to test PIV in the system, up to 225 with a fully developed inlet, no instabilities there. So the aim of this slide is to tell you that, first of all, people have looked at this for a very long time, but there's no real consensus as to what happens, because I can probably say here instabilities exist somewhere between 359 and 1,500. Now, I'm an experimentalist, so I'll tell you what the experiment is. We have a pipe which expands from 8 millimeter diameter to 16, so that's a 2-to-1 expansion. The upstream pipe is 1.23 meters long, which means we're fully developed at the separation point for Reynolds numbers up to 4,500, which is much higher than anything I'm going to tell you about. And then our downstream pipe is 0.95 meters as well. I said that 2 flow controls are used. We use a constant pressure head and a constant mass flux. The reason we use 2 systems, in fact, we had 2 different pipe systems as well, will become clear later. But that we change the drive. It doesn't really matter, all the data agrees from one system and the other. So that's our pipe. And when you have a pipe, so we've worked out what the experiment is, you now have to work out what visualization technique you want to use as well. And we were given the opportunity very kindly by Lynn Gladden in chemical engineering to come and use her MRI facility. I don't want to sound like a Barclaycard advert, but cost of the pipe is between 10 and 20,000 pounds of order. The cost of this is between 10 and 20 million pounds, and the cost of a purpose-built building to put it in with no magnetic materials in it is between 50 and 100 million pounds. So this is a very expensive experiment, and you probably can't get a grant to do this at home. Okay, I'm going to explain what the MRI technique is using a cartoon up here that I've drawn, and I'll explain before I start the movie. What we're interested in is the spins on our protons in our water, okay? So I'm a proton, here's my spin. What I'm going to do is I'm going to turn on a magnetic field to knock my spin over and then use a gradient to make it precess. Okay, so I'm a spin, I'm an excited spin, I'm precessing like this, and then I'm going to allow my system to flow for a small period of time and then rescan the same part of the flow and look for spin echoes and find out how much of the excited water molecules are still in my field of view. Now, this has got a very good resolution. You can probably compare it quite nicely to PIV. This can be used as stereoscopic PIV, it can be used similarly to holographic PIV. It is exceptionally powerful, but as I said, exceptionally expensive. So I'm going to show the movie so to give you an idea of what I mean. So here's my expansion, here's my slab of fluid I'm interested in. Have I started that? Let's start that, okay. So there are all my spins by water molecules. I'm going to use a magnet to align my spins, and I'm going to use a gradient to knock these over and make them precess. So this is now my water in this slab of fluid. The flow is going to occur for a short period of time, a few milliseconds, and now I'm going to use magnetic field again to look for spin echoes back in the same slab of fluid I was originally looking at in. And this means, in this particular technique here, I'm going to find areas with no or very slow flow, okay? So in this system here, this is what a typical MRI image would look like. I can see my pipe walls because of the no-slip boundary condition, and I can also see my shear layer in here as well. So I'd expect for this kind of flow to see two concentric rings. So what does this look like in reality? I'll say here, this is a typical image. I don't know if we can dim the lights. Can anyone dim the lights? That's fantastic, whoever that was. Here's our first image, Reynolds number of 406. Well, there's only one bright ring here. I said previously we would expect two. And the reason is we are 34.75 expansion step sizes downstream. So our recirculating eddy has not yet impinged into our field of view. And we'll see in the first few slides of this movie, as I increase the Reynolds number, we'll see the shear layer first of all impinge into the field of view. Okay. So we increase the Reynolds number. You can now see the start of the shear layer in the middle. Reynolds was increasing 800, 1,000, 1,200, and so on. And I don't know if any of you noticed that. I'll just play it one more time. But as I increase the Reynolds number, my shear layer first appears, but then it becomes asymmetric. It goes over to one side of my pipe, and I think it comes over to this side here. Now, as an experimentalist, you have to be very careful when this kind of thing happens, because the first question you have is how good is the experimental system, and the fairest answer, albeit the most expensive, is to throw the experiment away and build a new one, and that's what we did. So half the data I showed you was when Tom was spending a week in Cambridge, and then we threw the experiment away, and it's in the cupboard, and we made a completely new one, the same geometry, etc., etc. And I came down to Cambridge for a week, and we did the experiment again, and we got the same answer. Okay, so we're pretty happy that this is real. For a given system, yes, but in a different pipe system, it went over to a different direction. Okay, so what's happening is we've got a pitchfork of revolution, but if you add any small perturbation to this at all of these solutions disappear, and we're only left with one stable solution. This was shown by Golubitsky and Schaefer in 79, and what we can do experimentally is measure the asymmetry between my pipe walls and my shear layer. If I do that, this is asymmetry squared, so square plus the measure, you can see that this looks very much like a symmetry breaking bifurcation at a critical Reynolds number of 1,139 plus or minus 10. And those of you who aren't experimentalists, this looks like quite a good experimental bifurcation, okay? It would be good if we could actually tie in our results to what's been seen previously. So now we're going to use Mermaid in the flow as flow vigilant. And Mermaid is desiccated oyster shell or fish scales. And this follows the streamlines of the flow. And you can see at 1500, around 1500 or 1453, now we get this wave-like structure in the flow. And just to point out, our MRI was at this point here. This is where we were measuring. So with the MRI, we didn't measure this. And this is intermittent burst. It comes maybe once every 30 or 40 seconds, we'll see one of these. If I increase the Reynolds number further, and now I'm looking at this pixel line across here, you can see that my flow at the edges, my shear layer grows and shrinks periodically. And this might be evidence of a noisy hop. So I've not talked about turbulence or anything like that, but what I would say is, as a final remark, that if I increase my Reynolds number further, again, this is now 2000, that the flow does this, and we get this bursting phenomena. You can see that there. It's clearly very complex. Okay. So to wrap up, I will not play that again. I'll make a few remarks. Flow through a sudden expansion in a 3D pipe loses stability via a supercritical symmetry breaking bifurcation at this Reynolds number. I know a lot of people in the audience have looked at this problem numerically. I know from speaking to a lot, you want to look at this problem. This is what we find experimentally. We then see intermittency and then periodicity. And I thank you all. I'd also like to acknowledge very useful discussions with Andrew Cliff, and I would like to thank Lynn Gladden firstly for her invitation to her facility and also for her hospitality when we were there. Thank you.
Questions, comments?
Is your pipe vertical in the MRI?
Yes.
Let me be cynical. Are you sure it's perfectly vertical and not,
So with anything that we can measure using modern day techniques, yes. Mm-hmm.
Right.
In fact, horizontal is no good because if you do this horizontally,
you
find
stick it horizontally in the MRI.
Well, you can. They've got a horizontal one there as well.
Oh, really?
You can, but if it's horizontal, you can actually get convection starting before anything else, which naturally breaks the symmetry.
Okay, so could you say a little bit more about intermittency? Are you talking about a localized burst?
Right, I'll explain this in a bit more detail. So, what was that? So this wave here, that you can see, what we actually found was when we did the experiment, we didn't find a symmetry breaking bifurcation, we found intermittency at about 1100. Well, then what we found was as we removed more and more mechanical noise from the system, we clamped it to the ceiling, we did this, we did that this disappeared and revealed the symmetry breaking bifurcation. What happens is, at this point, it grows at this point here, it's not there, it starts at this point here, always the same point, you get this wave, and it sustains for maybe 5 or 10 seconds, and then disappears. When it disappears, it may detach and move downstream 1 diameter or something, but it goes pretty quick.
Then what happens when it becomes periodic?
When it becomes periodic...
stream of wave.
Sorry?
What happens when it becomes periodic then? What's periodic?
So periodic now is, as I said, if we just measure this pixel line across here with the actual absolute velocity, we see that the shear layer with respect to walls breathes in and out, if you want to call it breathing. That's a horrible word, I know. But,
Right.
So that's periodicity.
So then wave becomes periodic too.
What's the effect of the area ratio? Is there an effect
Of
for the sudden expansion?
yeah, of
You think there would be an effect of the area ratio?
the expansion ratio. Yes. What that is, I have no idea. And it's all very well experimentally. We could try every expansion ratio in the world, but now we've found this, we need numericists to feed back into us and tell us, first of all, whether or not it's realistically we can measure, whether or not we can measure something realistically. Okay. Well, yes, it will have an effect, because we know that as the expansion goes to zero, we get a parallel pipe. This can't be there.
Last question.
Do you need the MRI technique to see this?
So you could use whichever choose your technique. The MRI has the advantage over a lot of the other modern day techniques in that it is non-intrusive. We're not adding anything to the flow, we're not putting particles in. We know that what we see is what is happening. If we put the Mermaid in, we would, for asymmetry big enough, we'd see, with the Mermaid, we'd see the asymmetry in the shear layer then. But that just has not got the same resolution as this.
Okay, so let's start this